Okay, just to remind you from the last lecture, we're talking about molar mass. And molar mass means the mass in grams of 1 mole of anything. If we were to take the molar mass of anything in the macroscopic world, it would be so huge that it would be a useless concept. But it's great for tiny things like atoms and ions and molecules. These are submicroscopic. And so a mole, 1 mole, is equal to 6.022 times 10 to the 23rd of whatever we're talking about here. Atoms, ions, molecules. All right? And so we want to relate that to AMU, which is the mass of 1 particle. So here's what we learned. The molar mass in grams is numerically equivalent to the molecular mass in AMU. So it's going to be the same number. So if I take 1 molecule of water, we're talking about just one of these, okay? And we typically write that as H2O. 2 parts hydrogen, 1 part oxygen, all right? And so if I have what we call 1 molecule of the stuff, I'm just talking about a single particle. But if I multiply that times 6.022 times 10 to the 23rd, so that I have this many of these things, then I have the same number, 18.02, but my unit is now grams. 1 mole of water is equal to 18.02 grams. Okay, hopefully that's clear. So 1 molecule, we're talking about AMU. 1 atom of hydrogen, we're talking about AMU. 2 atoms of hydrogen, we're talking about AMU. Same thing for oxygen atoms. But if we're talking about 2 moles of hydrogen, we're going to measure that in grams. 1 mole of oxygen, we're going to measure that in grams, and 1 mole of water, we're going to measure in grams. So the numerical mass of water is equal to the mass of 1 oxygen and the mass of 2 hydrogens, whether we're in AMU for atoms and molecules or grams when we're talking about moles. So AMU, we're talking about atoms, molecules, and here with grams, we're talking about moles. Okay? All right. So the way that we compute this is the molecular mass. The mass of 1 molecule is 16 AMU. So this would be 16 AMU because we're talking about an atom of oxygen, and this is 2 times 1 atom of hydrogen. This is an atom of hydrogen. We have 2 of them, so that's going to be AMU as well. All right, 18.02 AMU is what that adds up to. But if we're talking about 1 mole, we're talking about 16 grams of oxygen. That means we're talking about 1 mole of oxygen. And if we're talking about 1 mole of oxygen, we're talking about 6.022 times 10 to the 23rd atoms of oxygen. That's what 1 mole is equal to. And the same thing over here, 2 times 1.01. We're going to be doing this in grams. And here we have 2 moles of hydrogen. Okay? So we actually have 2 times 6.022 times 10 to the 23rd atoms, and that's why we wind up with grams, because we're talking about a lot of those things. All right. So let's do some calculations. All right. So 1 molecule of water weighs 18.02 AMU. 1 mole of water weighs 18.02 grams. 1 mole of water contains Avogadro's number of molecules of water, and 1 mole of water contains 2 times Avogadro's number atoms of hydrogen. It's really just looking at the ratio, guys. The ratio is the same. H2O, 2 parts hydrogen, 2 hydrogen and 1 oxygen. Whether or not we're talking about a single molecule of the stuff, or if we're talking about moles of the stuff, remember, 1 mole of anything is equivalent to this number of whatever it is that you're talking about. 6.022 times 10 to the 23rd. In this case, 2 atoms of hydrogen. And 1 mole of water contains Avogadro's number. So we're talking about 1 mole of water molecules. These guys right here, molecules of water. And so guess what? 1 mole of water contains Avogadro's number atoms of oxygen, because in H2O it's a 2-to-1 ratio. And if we're talking about moles, that means I have 2 moles of hydrogen plus 1 mole of oxygen. And a mole, whether we're talking about 2 moles or 1 mole, every individual mole is equal to 6.022 times 10 to the 23rd. All right, this is going to take a little bit of time for you to wrap your brain around it, but I think you'll get it. All right, let's talk about this compound. Now, this is an ionic compound, and it's called magnesium phosphate. All right, so let's just imagine we have one, and I'm going to use the term molecule. Hopefully by now you understand that sometimes I'll use it for ionic compounds. So I'm imagining that I have 1 unit of magnesium phosphate, and all I want to know is how many magnesium ions there are, how many phosphorus atoms there are, and how many oxygen atoms there are, and maybe how many phosphate polyatomic ions there are in 1 unit. And all I have to do is look at the subscripts. So if I have just 1 unit, I have 3 magnesium 2+ ions. These are ions. Okay. Now, to figure out how many phosphorus atoms I have, I just take the parentheses like we've discussed, and I look at the subscript outside of the parentheses. I multiply all the subscripts inside the parentheses by the subscript outside the parentheses. If there's no subscript, I understand that's a 1. So it's just 2 times 1, and this is an atom, so that would be 2 atoms of phosphorus. Now, let's look at oxygen. If I have 1 unit of magnesium phosphate, I have 2 times 4, or 8 atoms of oxygen. Now, I can also say that since I have parentheses around this phosphate, I have 2 phosphate polyatomic anions, and these are anions because they're negatively charged. So I have 2 of those guys. Okay? All right. Now let's switch. Let's go to 1 mole of magnesium phosphate. all these ratios are the same. We're simply going to change our unit to moles. So that would be, if I have 1 mole of magnesium phosphate, I have 3 moles of magnesium 2 plus ion. If I have 1 mole of magnesium phosphate, I have 2 moles of phosphorus. And if I have 1 mole of magnesium phosphate, I have 8 moles of oxygen. Ugh. All right, and one more. If I have 1 mole of magnesium phosphate, I have 2 moles of phosphate. So that would be 2 moles of phosphate anions. Okay? All right. Now, let's think about what a mole means. 1 mole is equal to 6.022 times 10 to the 23rd of whatever it is we're talking about. So if I have 3 moles of magnesium 2 plus ions, that means I have 3 times Avogadro's number of magnesium ions, 10 to the 23rd, and that's magnesium 2 plus ions, okay? And these are cations. And then if I have 2 moles of phosphorus, that means that I have 2 times 6.022 times 10 to the 23rd atoms of phosphorus. And if I have 8 moles of oxygen, that means I have 8 times 6.022 times 10 to the 23rd oxygen atoms. And finally, if I have 1 mole of magnesium phosphate, I have 2 moles of phosphate, and that means I have 2 times 6.022 times 10 to the 23rd phosphate anions. Okay? All right, just as a review, 1 mole of magnesium phosphate contains Avogadro's number molecules of magnesium phosphate, 6.022 times 10 to the 23rd. 1 mole of magnesium phosphate contains, remember the look at the ratio, it's a 3-to-1 ratio, 3 magnesiums for every 1 magnesium phosphate. So that tells me I've got 3 times Avogadro's number of ions of magnesium. And 1 mole of magnesium phosphate contains 2 times Avogadro's number atoms of phosphorus, because the ratio for 1 mole of magnesium phosphate, I have 2 moles of magnesium. And every single mole is equal to Avogadro's number. So that's 2 times Avogadro's number atoms of phosphorus. 1 mole of magnesium phosphate contains 8 moles, or 8 times Avogadro's number of oxygen. 1 mole of magnesium phosphate contains 2 times Avogadro's number of phosphate ions, because the ratio is 2 moles of phosphate for every 1 mole of magnesium phosphate. 1 molecule of magnesium phosphate. Now notice I've stepped down. I've gone down to a single unit of magnesium phosphate. It contains 8 atoms of oxygen. So that's just 2 times 4, or 8 atoms of oxygen. If this had been moles, then this would have been 8 times Avogadro's number, because 1 mole is equal to Avogadro's number. All right, so let's ask this question. How many moles of oxygen atoms are there in 6 moles of this compound? This is aluminum sulfate, an ionic compound. And so here's how you do it. Do it like you would a dimensional analysis problem. You have an X factor. The how many moles is your X factor. This is moles of oxygen. Now, I know it says atoms down here, but we don't need Avogadro's number because the how many part is how many moles. And so this is how many moles of oxygen. Well, if I had 1 mole of aluminum sulfate, I would have 3 times 4, which is 12 moles of oxygen. But I don't have 1 mole, I have 6 moles. That's what goes on the other side of the equal sign. So this is just going to be Al2 parentheses SO4, and then I'm going to throw a 3 out here. Now I come up with my conversion factor, and my conversion factor is nothing more than the ratio of moles of aluminum sulfate to moles of oxygen. And that's a 3 times 4, which is 12 to 1 ratio. So for every 1 mole of Al2SO4, whoop, that's a 3, I have 12 moles of oxygen. And so my problem is now simple. Moles of aluminum sulfate over moles of aluminum sulfate cancels. And so it's just 6 times 12, which is 72 moles of oxygen. And that's my answer. Okay, 72. Okay, so don't be fooled by this. If you're given moles and you're asked for moles, you don't need Avogadro's number. You're just using the ratio, and you're going from mole to mole. So all it is a ratio. Which of the following statements is true? So this is just a question to see if you understand the nature of what a mole is, what a molecule is, and the appropriate units that you would use to describe or answer the question. All right? So each is a question in itself, a true-false question. So this is a true-false question. So let's ask the question. A mole of calcium phosphate contains 8 moles of phosphorus. Well, 1 mole of calcium phosphate contains 2 times 1, or 2 moles of phosphorus. So this is going to be a false statement. 1 mole, a mole of, this is an ionic compound called iron 3 nitrate, and it says it contains 9 times Avogadro's number atoms of oxygen. Well, what you want to think about is this. This is equal to 1 mole. So Avogadro's number is just referring to a mole. So let's ask ourselves the question. If I have 1 of these, iron 3 nitrate, this would be 3 times 3, which is 9 moles of oxygen. And if I have 9 moles of oxygen, that's equal to 9 times 6.022 times 10 to the 23rd atoms of oxygen. And so that is a true statement. So that's going to be our answer. This is true. It has 9 times Avogadro's number atoms of oxygen. Let's take a look at this. If it says molecule, it's referring to 1 unit of this stuff. Now, if it's 1 unit of this stuff, a molecule, and this is aluminum chloride, contains 3 times Avogadro's number. Well, if it's just a single unit, you don't have Avogadro's number of chloride ions. You just have 3 chloride ions. You've got 1 aluminum 3+ ion, and you've got 3 discrete chloride ions. And that's where that formula comes from. And we're talking about molecules, so we're talking about 1 unit. So this statement is false. A molecule, as soon as you see molecule, you know you're talking about 1 unit of. So if anything refers to Avogadro's number, you know, well, that can't be true. Okay? And this is sodium sulfate, and another ionic compound, contains 4 sulfate ions. Well, this is a little different question. This is asking you how many of these guys, sulfate ions, are in 1 unit of sodium sulfate. And we can see that we do have 4 oxygen atoms because there are 4 oxygen atoms in sulfate, but this is an understood one. And keep in mind, you do not use parentheses around polyatomic ions unless you have more than 1 of them. Okay, so it would not be appropriate to put parentheses and a 1 out here. Okay, you just write it as sodium sulfate the way that it was written. Well, I better erase that or I will confuse some people. So you don't have 4 sulfate ions, you just have 1 sulfate 2- ion. So how many molecules of ozone are in 1 mole of ozone? Well, that's pretty easy because 1 mole is equal to 6.022 times 10 to the 23rd of whatever you're talking about. And if we're talking about ozone, that means that we're going to have 6.022 times 10 to the 23rd of this stuff, molecules of O3. And just so you know, O3, ozone, it's a peculiar molecule, non-bonding electrons here, 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 and here, and another pair sitting up here. That's the ozone molecule, guys, and this guy protects us from UV radiations. It's up in the stratosphere. When the UV hits it, it splits up into O2. So it takes 2 of these and it'll split up into 3 O2 molecules. All right, how many grams does 1 mole of ozone weigh? This is a big deal. We're going to go to the periodic table of the elements to find out. So here's oxygen, and here's what I want you to notice about oxygen. Down here, it's atomic number 8. It means it has 8 protons in the nucleus. And its atomic mass, or its molar mass, the mass of 1 mole, is going to be 15.999 grams. And we have 3 of them when we're talking about ozone. So let's go back to the PowerPoint notes. Okay, so that means that 1 mole of ozone is equal to 3 times the molar mass of oxygen. And the molar mass of oxygen we can safely round to 16.00 grams. And 3 times 16 is 48.00. And here's how we say it: grams per mole. So how many grams does 1 mole of ozone weigh? It weighs 48.00 grams per mole. This is how we describe the concept that we call MM, or molar mass. And you want to remember the unit. We write it as grams per 1 mole. That's what molar mass means. Grams per 1 mole. How many molecules of ozone are in 15 grams? Now here's the cool thing about molar masses. I can weigh ozone and I can determine using Avogadro's number and the molar mass of ozone, I can determine how many molecules of ozone I have in those 15 grams. I can determine how many atoms I have in some amount, 15 grams of ozone, etc. All right, we're going to do this step by step. How many molecules of ozone are in 15 grams of ozone? So you want to remember that molecules is a microscopic quantity. Okay, you're talking about really tiny stuff. And grams, that's something you can go weigh in the laboratory. So this is a macroscopic quantity. All right? And what we want to do is we want to go from a macroscopic quantity of 15 grams to a microscopic quantity. So we're going to do it in dimensional analysis format. We're going to write X molecules of ozone, and that's going to, and this is microscopic, okay? Molecules is micro. And then on the other side of the equal sign, 15 grams. And this is a macroscopic quantity. So you're going from a macroscopic quantity, and we will wind up with a microscopic quantity. So here we go. The first thing you do is you convert grams to moles. Okay, so we're going to convert grams of ozone to moles of ozone. And every 1 mole of ozone, we already figured it out, is 48.00 grams. This allows us to convert the 15 grams of ozone into moles of ozone. Now, we're still in a macroscopic world. Moles is a macroscopic quantity. We've got Avogadro's number of ozone molecules here. But we're going to quickly go from moles of ozone to the number of ozone molecules, 6.022 times 10 to the 23rd, and this is molecules of ozone, okay? All right, so let's just check the units out, make sure everything works. Grams over grams cancels. Moles of ozone over moles of ozone cancel, and we wind up at the end with molecules of ozone. And that gives me 1.88 times 10 to the 23rd molecules of ozone. Okay, I've gone from the macroscopic quantity of 15 grams to the microscopic quantity of molecules. So molecules is microscopic. So here's how that process works. If you're given grams, divide by the molar mass, and we use m for molar mass, and then all you have to do is multiply times Avogadro's, this is a G, Gadro's number. Okay, 6.022 times 10 to the 23rd. So that's going from grams to molecules. All right, so now let's ask the question, how many oxygen atoms are in 15 grams of ozone? Well, I could start over. As a matter of fact, I think I will start over. I could, since I know I have molecules of ozone, this is a 3-to-1 ratio. I could just multiply that number by 3 and I would be good to go. But let's go ahead and get a little bit more practice. Here we want to do atoms of oxygen. We'll go back to our 15.0 grams of ozone. We'll divide by the molar mass, which is 48.00 grams for every 1 mole of ozone, and then every 1 mole of ozone, I'm actually going to do it a little bit differently. I'm just going to look at the ratio of oxygen to ozone. And you can see that it's 3 moles to 1 mole, since there are 3 moles in 1 molecule of ozone, or in 1 mole of ozone. So I could say there are 3 moles of oxygen. Now, I could have gone from moles of ozone to molecules of ozone, and then I could have gone from 1 molecule of ozone to 3 atoms of oxygen. And it would have worked out exactly the same way. You can play around with this. So every 1 mole of oxygen is equal to 6.022 times 10 to the 23rd, and this is atoms of oxygen. Tend to write all the units so that I don't confuse myself. Grams of ozone, cancel. Moles of ozone, cancel. Moles of oxygen, cancel. And so I wind up with 5.65 times 10 to the 23rd atoms of oxygen. All right. So in truth, what I actually did was I just took this number and multiplied it times 3. The math would work out exactly the same way as the way that I've set it up here. So just play around with that and you'll get it. Okay, so our next question is, how many sulfur atoms are there in 1.65 grams of aluminum sulfate? First thing to notice that this is grams and this is a macroscopic quantity. And we're going to go from a macroscopic quantity to a microscopic quantity, and atoms are definitely microscopic. So we're going from macro to micro. So here's the way it's going to work. We need to divide by the molar mass. Okay, so that's going to be the first thing we need to do. Divide the 1.65 grams by the molar mass of aluminum sulfate. Then we're going to do a mole-to-mole ratio. Since we're talking about sulfur atoms, it's going to be a 3 moles to 1 mole. It's going to be 1 mole of aluminum sulfate to 3 moles of sulfur. And then so this will be a mole-to-mole ratio. And then what we're going to do is we're going to multiply times Avogadro. So that's our plan. Well, in order to do this, we need a molar mass. So we need to go to the periodic table. Now, I got the periodic table memorized with respect to a few elements, so let's go ahead and let's figure out the molar mass for aluminum sulfate. There are 2 aluminums. Each mole of aluminum weighs 26.98 grams. There are 3 moles of sulfur, so this is going to be 3 times 32.07 grams, because every 1 mole of sulfur weighs 32.07 grams for every 1 mole. And then there's 3 times 4, which is 12. That's going to be 12 times 16 grams per mole. And so let's work that out. So the molar mass of aluminum sulfate will be 2 times 26.98 plus 3 times 32.07 plus 12 times 16 for a grand total of 342.17 grams per mole. So 342.17 grams for every 1 mole of the stuff, okay? So this is the molar mass of aluminum sulfate, the mass in grams of 1 mole of that compound. All right, I'm going to make a little bit of room for myself, so you can stop the video and you can write all of that down if you like. Okay, so our how many part is sulfur atoms. So that's going to be X sulfur atoms. And that's definitely microscopic. I've got a macroscopic quantity of 1.65 grams of Al2SO4 3. Now, my conversion factor here is to divide by the molar mass, which we figured out was 342.17 grams for every 1 mole of Al2SO4 And my next conversion factor, because this is going to get rid of grams. I'm now in moles of aluminum sulfate. And 1 mole of Al2, parentheses, SO4 is equal, and what am I looking for? I'm looking for sulfur atoms. So that's going to be a 3 sulfurs for every 1 mole of aluminum sulfate. So that's 3 moles of sulfur, and then 1 mole of sulfur is equal to Avogadro's number of sulfur atoms, which is 6.022 times 10 to the 23rd sulfur atoms. Let's check the units. Grams of aluminum sulfate, cancel. Moles of aluminum sulfate, cancel. Moles of sulfur, cancel. And we're left with atoms of sulfur. And so, here we go. 1.65 divided by 342.17 times 3 divided by 1 times 6.022 to the 23rd. And that gives me, it looks like 8.71 times 10 to the 21st. So 8.71 times 10 to the 21st atoms of sulfur. And that would be our answer. So we're going from macroscopic to microscopic. We divided by the molar mass. We looked at the ratio of moles of sulfur to moles of aluminum sulfate. It's a 3-to-1 ratio, and then we simply multiplied by Avogadro's number. So if you're going from macro to micro, all the way from grams to atoms, you're going to divide by the molar mass, do the mole-to-mole ratio, and then multiply by Avogadro's number. What I would suggest is that you take this very same problem and you work it in reverse. You go from atoms of sulfur to grams of aluminum sulfate, and you should get 1.65 to 3 significant figures, okay? And it's 3 sig figs.